So now that we've talked about the basic Java completable future features, let's take a look at a case study that illustrates how to apply those features. And this case study will work in the context of the so-called big fraction class that we've looked at before. We'll also spend a little time talking about some of the limitations with these basic features, which of course motivate the more advanced features we'll talk about next. So this example is similar to one we looked at before. We looked at this before in the context of Java futures, where it did the same thing, but it was a bit more syntactically awkward to write because it wasn't as well integrated with all the cooler completable future features. Again, this is just the basic stuff, however. So we're going to show an example that multiplies big fractions using the completable future framework. And on the left-hand side, we'll look at the code. On the right-hand side, we'll show an interaction diagram that illustrates who's talking to whom and when. So the first thing that happens here is we make a new empty completable future. It doesn't have any actions associated with it. It's essentially incomplete. And you can see here how that corresponds to having the main thread of control create a new instance of completable future. We then go ahead and create a new thread and start it. So this will run a computation, which I haven't highlighted yet, but will shortly. And that computation will run in a background thread. So you can see here the main thread creates a background thread and starts it. And then the runnable, which in this case is a lambda, will be invoked to run in the context of that background thread. Now, here's the computation we're going to give. This is a runnable lambda expression, which corresponds to the parameter that you would pass in. Note how nice and condensed this is. We don't have to create a special class and make an instance of it. We don't have to make an anonymous inner class, which is horrible and syntactically verbose, and so on. So this particular approach will multiply big fractions using big integers. So you can see that we have two big fractions, which are given nice big values. And in the background, we multiply big fraction 1 by big fraction 2. And that computation that is shown in red here, and whatever happens to be going on in the calling thread, which I show as ... those things will run concurrently. And you can see here that that's what's happening. The main thread's running, the background thread's running, they're doing stuff. And then, after the multiplication finishes, and if you have a big enough set of big fractions, it'll take a while to do that, then we complete the future. So that's kind of like the donut hole in the donut. It completes the future, and that will explicitly complete it, and it passes the result to the future. So now the future's been updated with the completed result. You can see what that looks like over here. And now the main thread, which could be off doing various things, it might run for a while, but at some point it can't make any further progress until it gets the result. It calls join on that future, that completable future, and that join call will block until the result is computed in the background, at which point it will go ahead and convert the result into a so-called mixed fraction. So it takes it from an improper reduced fraction into a mixed fraction. Now, that's the example, pretty simple, but sadly there are some limitations with this approach. And the key problems here are that this set of features in completable future don't really address all the limitations we identified earlier with Java future. They only identify a very tiny little thing. And in particular, they don't address issues of chaining things fluently to handle async results. We don't show how things are triggered reactively. And we're not talking about how you can efficiently treat a completable future as a collection of completable futures. So we really haven't solved any of the problems with Java future. And that's no surprise because the basic features in completable future are the same as the ones in future. So just to underscore this, this code also uses blocking. And the problem with blocking, as we'll talk about a number of other times, is it underutilizes processor cores by tying up a thread that could be doing something else, and it increases the overhead because you have to wait for things to synchronize and combine and join and merge and so on. Moreover, we are not in a position to use timed operations because join doesn't have a timed operation. So if we use get in this case, then we have to figure out how long to wait, which is tedious and error prone. And then, of course, we'd have to throw some kind of exception handling mechanism in here because get is a checked exception. So it's inefficient, it's error prone, it's ugly, and so on. So of course, this is all leading up to, drum roll please, why we need to have more advanced features that are provided by CompletableFuture, which is what we're going to do. So rather than the simple knife, fork, and spoon set that we showed earlier for basic features, we're going to have the Swiss Army knife capabilities that come with the advanced features of Java Completable Futures. But it's important to understand how to use these basic completable features because you may see them at some point if you're working on code bases by people who don't really understand the more advanced stuff.